All right, hello everyone. Now we're going to talk about section 8.2, which is about combinations. So we know in our last section, section 8.1, we talked about the multiplication principle and permutations. So now this is just going to be another extension of those concepts. So for starting, let's say we are selling a mystery book, a biography, and a textbook at a book sale. The following 6 arrangements are the different ways in which the books can be sold. So we have mystery book, biography, textbook, mystery, textbook, biography, biography, mystery, textbook, biography, textbook, mystery, textbook, biography, mystery, textbook, mystery, biography. So these are all the different ways that we can rearrange our 3 different books. So this shows the 6 different arrangements of 3 books, or 6 different ways in which the books are sold. But there's just one set of 3 books. So a subset of items listed without regard to order is called a combination. And this is going to be written as C of NR. So we knew our permutation was written as P of NR. So now our combinations are written as C of NR. Since they are just subsets, they are not ordered like how permutations are. So we know that permutations are listed in order, like how we see these 6 different arrangements here that we listed for our books. These are permutations because they take into consideration the order of how they are formed. But with our combinations are just going to be subsets. And remember, when we learned about subsets, we considered subsets to be the same even if they had different orders. So with combinations, we don't care about the order. Permutations, we do. So using example 4 from section 8.1, the example that we said that we'd be using in the future, we remember that we had 8 books and we had to fill 5 slots. So to evaluate our combination of 8 and 5, or a C of 8, 5, we start with the 8 times 7 times 6 times 5 times 4 permutation of 8 books taken 5 at a time. Remember, that is how we ended up solving that, since we had 8 books and we took 5 slots and we had 1 less option every time. Since combinations are not ordered, we find that the number of combinations by dividing the number of permutations by the number of ways each group of 5 can be ordered. Or just in other ways, we divide by 5 factorial. So what we see here is that when we have our combination, we take that permutation that we had, that was the 8 times 7 times 6 times 5 times 4. We take that value and we're going to divide by 5 factorial, since we know that each group of 5 can be reordered. So when we do this, we see that we have numbers in common once again, which are going to be 5 and 4. So we can cancel out our 5s and our 4s. And what we're left with is 8 times 7 times 6 divided by 3 times 2 times 1. When we calculate this value, we're going to end up getting 56. So this means that there are 56 different combinations of ways that the teacher can place 5 books on her bookshelf. And remember, the value that we found for our permutations was definitely different, and that's because we could have ordered them differently. But with combinations, we don't care about the order. There are just 56 different combinations. So our official definition here for combinations, we have if our combination of n and r denotes the number of combinations of n elements taken r at a time, where r is less than or equal to n, then our C of n comma r is equal to n factorial divided by n minus r factorial times r factorial. So by looking at this, our equation is very similar to our permutation equation. The only difference here is that we're now dividing by our value of r factorial. That's the only difference. And by doing this, we are essentially factoring out the order of our permutation. That's how we find our combinations. So once again, I'm going to show you the proof just so that you have kind of a reference of how we ended up finding this, this formula, but you will not be tested on the proof or anything along those lines. It is just nice to look at and reference if you would like to know how we ended up getting this formula. So we say generalizing this discussion gives the following formula for the number of combination of n elements taken at r, or taken r at a time. So essentially, this is our combination of n and r is equal to the permutation of n comma r divided by r factorial, which is what we did before when we took our values of 8 times 7 times 6 times 5 times 4 and we divided by 5 times 4 times 3 times 2 times 1. Another version of this formula can also be found. So we have our equation of combination, so C of n and r is equal to our permutation of n comma r divided by r factorial. So basically what we want to do is just set our permutation equal to its actual equation, and when we do that we get n factorial divided by n minus r factorial. It's going to be multiplied by 1 divided by r factorial. We have the original equation here for our permutation. You don't quite remember. So then when we simplify it down, we just get n factorial divided by n minus r factorial times r factorial. So that's how we end up getting our combination formula from our permutation formula. All right, so let's do our first example with combinations. So example 1 here is how many committees of 4 people can be formed out of a group of 10. So we have a total or n value of 10 people, and we want 4 committees, we want committees of 4 people. Sorry, I switched the words there. So committees of 4 people, so we have 10 in all and we're taking 4 at a time. So we know that our R value is going to be 4. Now since we know our value of n and we know our value of r, we can just plug this into our equation. We know that C of n comma r is equal to n factorial divided by n minus r factorial times r factorial. So this means that C of 10 comma 4 is equal to 10 factorial divided by 10 minus 4 factorial times 4 factorial. And that's how we're going to write this out. And now we can simplify a little bit and we end up getting 10 factorial divided by 6 factorial times 4 factorial. Now, what we can do here is that if you have an online calculator, you can plug this value straight into an online calculator because it knows what it's doing. If you have a graphing calculator, I do not believe you'll be able to input this value. But we're going to do it by hand because I want you guys to know how to do things by hand, just because you can always rely on it if you need to. So the values here aren't too bad, but what we end up getting is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So we have our 10 factorial here in our numerator. Now we want to do 6 factorial and 4 factorial. So if we do this, we end up with 6 times 5 times 4 times 3 times 2 times 1. And then we multiply that by 4 factorial, which is going to give us 4 times 3 times 2 times 1. So now we have all our values. And once again, we can cancel out some of our values. So we can definitely cancel out our 4 factorial, which is 4 times 3 times 2 times 1. But what we realize is that we can also cancel out our entire 6 factorial because every value in a 6 factorial is found in 10 factorial. So what we're going to do is cancel out each one of our values of our 6 factorial. So we can cancel 6, 5, 4, 3, 2, and 1. And when we rewrite this, what we end up getting is 10 times 9 times 8 times 7 divided by 4 times 3 times 2 times 1. Now we can write this again, and what we end up saying is 10 times 9 times 8 times 7 divided by 4 factorial, because we didn't cancel out a single value of our 4 factorial. So we could have just left this value as 4 factorial. We could have left it in this form the entire time. By the way, when we go to calculate this value, we're going to end up getting 210 ways, or 210 committees out of 4, or created of 4 people formed out of a group of 10. So 210 combinations. So just like permutations, you can also include combinations in your graphing calculator. It will also have a place where you could input that. It looks almost the exact same as permutation, except there's a C instead of a P. So we have graphing calculators have the capacity to compute combinations. For example, on a TI-84 plus C, or really any TI 80 something should probably have it. We have our combination of 8, 3 can be calculated by inputting 8 followed by NCR found in the math probability menu, and a 3 yielding 56. So your answer should end up getting 56, similar to figure 4 here. And this is what it should end up looking like in your calculator. All right. So example 1 shows us another way to compute our combination of n and r. So we want to take r or n minus r, whichever is smaller, and write it as a factorial. So whichever value you get that's going to be smaller, you just leave it in the form of factorial. So for our example, when we ended up subtracting 4 from 10, that gave us 6 factorial times 4 factorial, and then 10 factorial is being divided by that. So what we would do, since in this case our r is smaller than n minus r, we would leave our r factorial as r factorial without expanding it. Then what we would do is that we would just extend the numerator, and whichever term was larger in the denominator. And so this means that that 10 minus 4 factorial, which was 6 factorial, we're going to extend out our 6 factorial. Then this should make it so that there is one value in the numerator for every value in the denominator that has been extended, and then we could cancel them. So whichever value in the denominator that you extended, you should be able to cancel out every one of those values with the numerator, or at least a lot of them. So what we end up getting, an example here would be C of 10, 4, or C of 10, 6. So when we do this, we see C 10, 4. We get, just like before, we had 10 factorial divided by 10 minus 4 factorial times 4 factorial. That's going to end up giving us 10 factorial divided by 6 factorial times 4 factorial. So when we write this out, we're going to extend our 10 factorial, we're going to extend our 6 factorial, and then we're going to leave our 4 factorial just in our 4 exclamation point notation. But we're not going to extend it. Just like in our last problem, we know that that's going to give us 10 times 9 times 8 times 7 divided by 4 factorial. Then we can just calculate this value. We also see that if we have C of 10, 6, that's going to give us 10 factorial divided by 10 minus 6 factorial times 6 factorial. Now 10 minus 6 factorial, that's going to be 4 factorial. So what we're going to extend out is our value of r, which was 6. So remember, whichever one is bigger, that is the one you're going to extend out, whichever one is larger. So we end up with our same numerator. We have 10 factorial that is extended, and then we have 4 factorial left in our factorial notation, and we extend out our 6 factorial. This is going to end up giving us the same answer, which is 10 times 9 times 8 times 7 divided by 4 factorial. It's also going to be 210 combinations. So we do see that C of 10, 4 and C of 10, 6 are equal. They are the same number of combinations. So the number of ways to form a committee of 4 people out of 10 is equal to the number of ways to choose 6 out of 10 people that are not on the committee. Remember, this is not true for permutations. This is only true for combinations. So don't go and solve permutations thinking that this is the same thing. This is only going to work for combinations. But I also would say don't rely on this fact. Always try and make sure that they are equal to each other and solve them correctly. Don't always just assume this is correct. Definitely never with permutations. Only do this with combinations. All right, so moving on to example 2. We have from a class of 16 students, a group of 2 to 4 students will be selected to work on a special project. In how many ways can a group of 2 to 4 students be selected? So if we're thinking about this problem here, this is going to be similar to a problem that we had in our last section where we said no more than 4. By no more than 4, we meant 1 or 2 or 3 or 4. So in this case, if we're thinking of a group of 2 to 4 students, we know 2 to 4 students is equal to 2 or 3 or 4 students. So we need to find the number of ways for each case, in each case being 2 students, 3 students, or 4 students. And then we're going to add them. We're going to add them all up once we find the different ways in which we can, or the different combinations in which we can have 2 or 3 or 4 students. So we're going to see here our case, and then our combination. Okay, so with our first case, first things first, we want to say, since we know that the class has 16 students, we know n is equal to 16. Our total number is 16. So in our case of 2, or r equal 2, our combination is going to be c of 16, comma 2. So when we calculate this, we're going to get 16 factorial divided by 16 minus 2 factorial times 2 factorial. Then, when we have this, what we really don't want to do, now we're at the point where our numbers are large. We really don't want to write 16 times 15 times 14 times 13 all the way down to 1. We really don't want to do that. But we see that when we end up simplifying, we get 16 factorial divided by 14 factorial times 2 factorial. Now let's start expanding. So in our numerator, we have 16 times 15 times 14. And now we know our number of 14 is going to multiply down to 1. So remember the property that we learned in section 8.1, which was we can substitute out our values of n, or n times n minus 1 times n minus 2, up until we get to a factorial that we need. So in this case, we can write 16 times 15 times 14 factorial, and that covers the rest of our values down to 1. Then we see we have in our denominator 14 factorial times 2 factorial. So now we have a 14 factorial in the numerator and a 14 factorial in the denominator. And just like a regular value, we're just going to cancel them. Now what we end up getting is 16 times 15 divided by 2 factorial, which we know is just 2 times 1. So then we want to multiply these values, and when we simplify, we end up getting 120 combinations. So we see we could rewrite our factorial in the way that we wanted so that we could cancel out other factorials. All right, so now let's move on to our next case. So let's move on to r equal to 3. This is going to give us c is 16, comma 3 is equal to, and we'll do the same thing. We have 16 factorial divided by 16 minus 3 factorial times 3 factorial. This is going to give us 16 factorial times 13 factorial times 2 factorial. And we're going to now do the same thing, except we need to extend one value farther. So we're going to have 16 times 15 times 14 times 13 factorial. And that's a 3, not a 2. So now we have these values, and we can do the same thing as we did before. We can cancel our factorials. And we can do this because they're equal to each other, remember, not just because we have 8 factorial divided by 4 factorial equals 2 factorial. Remember, that's not a fact from section 8.1. That's not true. So, but we can divide by factorials if they are equal to each other because we know that they contain the exact same values. Now we end up getting 16 times 15 times 14 divided by 3 factorial, which is just 3 times 2 times 1. Now when we calculate this value, we're going to have 560 combinations. All right. Now lastly, let's do r equals 4. So we have our combination, 16 comma 4. This is equal to 16 factorial divided by 16 minus 4 factorial times 4 factorial. This is going to give us 16 factorial divided by 12 factorial times 4 factorial. And now we get to do the same thing again. We're just extending it one value farther. So we get 16 times 15 times 14 times 13 times 12 factorial. We're dividing by 12 factorial and 4 factorial. Just like before, we can cancel out our factorials. And we end up getting 16 times 15 times 14 times 13 divided by 4 factorial, which is going to be 4 times 3 times 2 times 1. And when we calculate that value, we're going to end up getting 1,820 combinations. Now also, just like our example in section 8.1, when we wanted to find 4 or less, essentially, we wanted to add up all the values. And we said this in the beginning too, we need to find the number of ways to use each case and add them up. So what we need to end up doing is adding up all these values, so we get 120 plus 560 plus 1,820. So we know that this is r equals 2, r equals 3, and r equals 4. And we get 2,500 combinations. So that's how many ways from a class of 16 students we can create a group of 2 to 4 students that will be selected to work on a special project. 2,500 different ways. A word of caution: when we're making a final decision when we're making a first decision and a second decision, we multiply to find the total number of ways. When we are making a decision in which the first choice or the second choice are valid choices, we add to find the total numbers of ways. So when we're thinking or, we want to add. If we're thinking and, we want to multiply. Essentially what we want. So the formulas for permutations and combinations are going to be very useful in solving probability problems in our next section, section 8.3. So it's very important to know the difference between them. We really want to know exactly how they're different and when to use them in order to solve our probability problems that were going to be more difficult in our next section. So just kind of like a little chart here that shows us and really goes over what the differences are. So starting with permutations, we have different orderings or arrangements of the R objects are different permutations. And then we have, of course, our equation, which is P of n comma R is equal to n factorial divided by n minus R factorial. The clue words here to use are arrangement, schedule, and order. And this is because order matters. So the order matters for permutation. So whenever you see the words in a question, like arrangement, schedule, order, automatically you should think permutations. I need to do permutations. Then for combinations, we have each choice or subset of R objects gives one combination. Order within the group of R objects does not matter. Order doesn't matter for combinations. Then we know our combination or combination formula here is C of n comma r is equal to n factorial divided by n minus r factorial times r factorial. The clue words for combinations are going to be group, committee, set, or sample. And this is because your group or committee or set or sample are not ordered. It's just a collection of elements or collection of people or whatever you're thinking about. It's your collection of elements and the order doesn't matter at all. The best way to think about it is that permutations care about order and combinations don't. That's the easiest way to think about it. So when you're given an equation or you're given a problem, the main question to ask yourself is, do I care about the order? If you do, you need to use the permutation formula. If you don't, you use the combination formula. And also these keywords, these really help you as well when you're reading questions because then it can pretty much tell you exactly what you're asking for. All right, so now that we've gone over the difference and the importance of the difference, let's move on to example 3. So for example 3 here, we're just going to decide whether each situation involves a permutation or a combination, and then we're going to solve. So for problem A, we have marbles are being drawn without replacement from a bag containing 16 marbles. How many samples of 4 marbles can be drawn? So what we're asking here is that we have a collection of marbles we're drawing without replacement, and we want how many samples, 4 marbles, can be drawn. Let's look at our keywords here in permutations and combinations. We're really thinking about the word samples. How many samples, 4 marbles, can be drawn? In permutation, our clue words are going to be arrangement, schedule, and order. So we're not really thinking about samples for permutation, but if we look at combinations, our clue words have group, committee, set, or sample. So since we see that clue word there of sample, this tells us we're going to use a combination. We also know that since we just need 4 samples of marbles, we don't care about what order they're in. So we can say here, we want the number of samples, we could say, or combinations, of 4 marbles so let's use the combination formula. So remember, since it's combinations or samples, no order. All right, so we know we're going to be using the combination formula, which we know is going to be C of n comma r is equal to n factorial divided by n minus r factorial times r factorial. We know our n. In this case, we have 16 marbles, so our n is going to be 16. And we're drawing samples of 4 marbles, so we know our r is going to be 4. So when we write this out, we're going to take C of 16 comma 4, which coincidentally is one of the things that we solved for in our last example here. We had 16, 4, but now we just get to do it again. So we take 16 factorial divided by 16 minus 4 factorial times 4 factorial. Now we simplify to get 16 factorial times 12 factorial times 4 factorial. Now remember, we're going to extend out our numerator so that we can end up canceling with our larger factorial in the denominator. We know this gives us 16 times 15 times 14 times 13 times 12 factorial. And we have 12 factorial and still 4 factorial. We see here, we can find that our 12 factorials will cancel. We get 16 times 15 times 14 times 13 divided by 4 factorial, which is 4 times 3 times 2 times 1. And when we simplify this, just like our last time, we had 1,820, and in this case, we're thinking samples. So 1,820 samples. All right. Now for part B, in how many ways can 5 out of 9 plants be arranged in a row on the windowsill? So, reading this again, in how many ways can 5 out of 9 plants be arranged in a row on the windowsill? Now let's go back up to our chart here. Let's look at our clue words for permutation. The first word we see is arrangement. Our question specifically asks how many ways can things be arranged. So this word is going to tell us permutation. Just like how the word samples told us combination. All right, so now we know for part B, we're definitely going to be using our permutation equation. So we can say we're looking for arrangement. So let's use the permutation formula. Then we're going to say n is equal to 9 and r is equal to 5, since we're taking 5 out of 9. Then we know our permutation formula of n comma 5 is going to be equal to n factorial divided by n minus 5, sorry, 9 minus 5 factorial. So 9 factorial divided by 9 minus 5 factorial. I think because I started at the letter n, I just said n. But yeah, we have 9 factorial divided by 4 factorial. 9 minus 5 is going to be 4 factorial. So you can either plug this into your calculator using a graphing calculator or an online calculator and solve for this value. I'm going to write it out by hand. We end up getting 9 times 8 times 7 times 6 times 5 times, and then we know we're going to have 4 times 3 times 2 times 1, which is 4 factorial. We're dividing by 4 factorial, so we can cancel these values. So all we're left with is 9 times 8 times 7 times 6 times 5, which when we multiply these out, it's going to be 15,120 different ways. 15,120 ways we can rearrange 5 out of 9 plants in a row on a windowsill. And we can also see that we're going to end up with a lot more permutations than we get with combinations, and that's because we care about the order when we don't care about the order in combinations, but we do in permutations, so we're going to have a much larger number of ways we could do this. All right, and then for our last one here we have C. So a group of 3 students is to be selected from a group of 14 students to take part in a cell biology class. How many ways can this be done? Let's read it again. A group of 3 students is to be selected from a group of 14 students to take part in a cell biology class. So let's look at our chart, look for some clue words here, and the first thing we see under combinations is the word group. Since we see that it's the word group, and we know it's just a group of 3 students is to be selected from another group of 14 students to take part in cell biology class, we know that order doesn't matter, because it could be any group of 3 students. So we know that the word group, and we're really paying attention to this first term, group, is going to be equal to combination. Then we can say we're looking for a group of 3 students. Order doesn't matter, so let's use the combination formula. So we can say that n in this case is 14 because we have 14 students in all. Our R value is going to be 3 since we're taking a group of 3 students, so we're taking 3 at a time out of 14. And we set up our combination equation. So we have our combination of 14, comma 3 is going to be equal to, we know this is going to be, let's move this down, 14 factorial divided by 14 minus 3 factorial times 3 factorial. And we get to do the same thing. Let's simplify. So we get 14 factorial divided by 11 factorial times 3 factorial. As always, you can plug this straight into an online calculator if you would like, but I'm going to do this by hand. So we get 14 times 13 times 12 times 11 factorial, which matches. In this case, we have 11 factorial in our denominator and 3 factorial. So let's cancel out our 11 factorials. Then we end up with 14 times 13 times 12 divided by 3 factorial, which we know is 3 times 2 times 1. And then when we multiply these values out, we end up getting 364 different ways we can select a group of 3 students. All right, so that was purely just identifying like what kind of clue words we need so we can decide on what kind of formula we can use, whether it be permutation or combination. All right, so moving on to our next example, we have example 4, which is also your turn 4. And what we're going to do is we're going to read each scenario here, and then we're going to solve. So for A here, we have, in how many ways can a committee of 3 be chosen from a group of 20 students? So if all we're thinking about is a committee of 3 being chosen from a group of 20 students, if we're just thinking about a committee, the order doesn't matter. There's no need to differentiate who had what place if it's just a committee of 3. So let's say that. So we say there's no reason to differentiate among the 3 in the committee. So let's use our combination formula. All right, so if we use our combination formula, we're going to say that our entire group we know is 20 students. So we say n is equal to 20. We're choosing 3 to be on a committee. So we're taking 3 at a time. So our R is equal to 3. And we know we need to use our combination formula. So we have combination of 20 comma 3. This is going to be equal to 20 factorial divided by 20 minus 3 factorial times 3 factorial. I didn't need a line that large. So now let's simplify. As always, we get 20 factorial divided by 17 factorial times 3 factorial. Once again, if you have an online calculator or you would like to calculate this value just from this point on, feel free to do that, but we'll do it by hand. So when we separate this, we get 20 times 19 times 18 times 17 factorial. And we're divided by 17 factorial times 3 factorial. And once again, we can calculate our 17 factorials, make our lives a little easier, and we end up getting 20 times 19 times 18 divided by 3 factorial, which we know is 3 times 2 times 1. And let's bring our answer down here. When we calculate this value, we're going to end up getting 1,140 different ways to create a committee of 3 out of 20 students. All right. Now, taking the same situation, we're going to say, in how many ways can 3 officers, so a president, a treasurer, and a secretary, be selected from a group of 20 students? So it's the same kind of idea, but now we need to differentiate. So if we're thinking of 3 different officers, we know that these 3 students need to be assigned roles, be assigned different roles, or in other words, they need to be arranged by role. So they'll be arranged in a separate way. So now that we know that they'll need to be arranged by role, let's use our permutation formula. All right, so now we're finding the permutation, and we still have that n is equal to 20 and r is equal to 3. So we have our permutation of 20 comma 3, which we know is equal to 20 factorial divided by 20 minus 3 factorial. It's going to give us 20 factorial divided by 17 factorial. And like before, we know we can extend out, our numerator in order to be able to cancel out our 17 factorials. All this leaves us with now is 20 times 19 times 18. And when we simplify this and multiply these terms together, we get 6,840 ways now that we can choose 3 different officers out of a group of 20 students. So this one was a little bit trickier since we didn't really see those clue words. We didn't have a clue word, but we had to think about, was order necessary? Order is now necessary since we need to differentiate between each student in the committee. So now we would think of the different orders in which we would have president, treasurer, secretary, and then all the different combinations of the students we can have. All right. So as a word of caution here, it should be stressed that not all counting problems lend themselves to either permutation or combinations. When a tree diagram or the multiplication principle can be used directly, it's often best to use it. So just because we have a question doesn't necessarily mean that we need to use combination or permutation. Sometimes it is just best to use a multiplication principle. And that's basically like saying, if there's an easier way to do this, you should just use the easier way. No need to bother with a combination or permutation. All right, so for part A, for example 5 here, our last example, which is going to be number 45 in your book, we have 5 orchids from a collection of 20 are to be selected for a flower show. Part A is in how many ways can this be done? Part B is in how many ways can the 5 be selected if 2 special plants from the 20 must be included. So we're going to start with part A. So for part A here, so we're just picking out 5 of the 20 without any order. So we know we're picking a group of 5 orchids out of 20 to be in the flower show. So order is not necessary. So we know order isn't necessary. We're just picking a group of 5. So we're going to use the combination formula. All right, so we're using the combination formula. We have that n is going to equal 20 and r is going to equal 5 because we're taking 5 out of 20. So we get that our combination of 20, 5 is going to be equal to our factorial, or 20 factorial, divided by 20 minus 5 factorial times 5 factorial. Just like all the other times we're going to do it, let's simplify to 20 factorial to 15 factorial times 5 factorial. If you're using an online calculator or any other calculator, feel free to calculate the value at this point, but let's write it out by hand. We get 20 times 19 times 18 times 17 times 16 times 15 factorial. And we know we have 15 factorial in our denominator, times 5 factorial, so we can cancel out our 15 factorials in this case. And when we simplify this down now, we get 20 times 19 times 18 times 17 times 16, all divided by 5 factorial, which we know is 5 times 4 times 3 times 2 times 1. So now when we simplify this equation, we're going to end up getting 15,504 ways in which we can just pick 5 out of 20 orchids, just a group of 5. Now for part B, we want to know in how many ways can the 5 be selected if 2 special plants from the 20 must also be included. So now we're essentially saying that 2 out of 20 have to be included in the 5. So now this is a little different from the ones that we've kind of seen and been working with. But since we're saying, since we picked 2 orchids already for our flower show, we now have 18 options to fill in 3 slots. So we have 18 options and 3 slots that we need to fill. So now that we know this, or for the rest of the show, since we know the order of 13 still doesn't really matter, we say order of the remaining 3 doesn't matter since we already chose the first 2. We'll once again use the combination formula. All right, so we use the combination formula now since we know that the rest of our 3 doesn't matter. And we end up saying our combination of 18 out of 3. So now we have 18 out of 3 since we say that we have 18 options and we're picking for 3. So we have n is equal to 18 and r is equal to 3. So we're taking our combination at 18 and 3. We get 18 factorial, that doesn't need to be that big, 18 factorial, and then we want to divide by 18 minus 3 factorial times 3 factorial. We know we're going to end up getting 18 times 17 times 16 times 15 factorial, which we know we're dividing by 15 factorial times 3 factorial. And now we can cancel out our factorials. This is going to end up giving us 18 times 17 times 16 divided by 3 factorial, which we know is 3 times 2 times 1. And when we calculate this value, this is going to give us 816 ways that we can pick our next 3 orchids. All right, so that concludes our last example here for section 8.2. So we've gone over our new calculation formula, which is very similar to our permutation formula. Like we said in the very beginning, this section is really just kind of an extension of section 8.1. We learned a new formula and we learned the difference. And that was the main point really to get from our section 8.3 in this case. So it's going to be very important that we remember these concepts when we go on to our next sections, because we're going to use our permutation and combination formulas in order to find our new probability problems. So we're going to use these formulas to solve probability problems. All right, so like always, if you have any questions or concerns, feel free to send me an email, submit a question to our anonymous question form, or just pop into my office hours at any time. All right, I will see you all virtually later.